Okay, I have noticed that tutorial 3 is due today, even though it's a bonus points, but there are several things I didn't get a chance to cover. I mean, it's because of the Monday was a Labor Day break. That's why we didn't cover anything on Monday. But Friday, we still have to go through something else for homework 2, I think. But likely it's not due yet, right? It's due tonight. I'm gonna work on it. I'll go through the problems, make sure you guys can get the correct answers, okay? How is the pace? Okay? Feels like it's pretty fast. Homework 3 is due the 6th, which is, I think it's 6, right? 2 days from now. We'll go through it definitely today as well, cover as much as we can. Crazy. Don't know how other students in other sections are doing well as well, or do you know anyone in other sections? So many problems to cover. So let's do it. First, you need to know the differences between voltage dividers and current dividers. So the voltage divider equation is based on the same current of the branch. The ground here is V in. If you label this as VL, this is R1, this is R2. It's just a one model, but you can apply this model to all different types of circuits. If you just convert the resistors, combine the parallel resistors or series resistors in several steps. So for this case, because it has the same current, so VL over V in becomes what? So you have to put a VL on the top. So VL is basically I, the current flows through the R2, causes a voltage drop, which is I, R2. So V in is the overall voltage, so it's the current flows through both resistors, it's I times R1 plus R2. And you cancel R because it's the same current, like I said, same current. So this equals R2 over R1 plus R2. So if you do it quickly, every time you see a circuit like this, every time you see a circuit like this, you can directly write down VO equals VI times R2 over R1 plus R2. This will simplify the calculation a lot. This is a voltage divider theory because they share the same current. And I gave you guys one example, I think last week. If I have R3 here, I got two parallel resistors. Can I still write down the voltage divider equation like this? VO equals VI times R2 over R1 plus R2. Sometimes you'll see a more complicated resistor network. Can you still simplify the results like this? So you are looking at V in, which is the overall voltage, and here's the voltage across R2. Definitely it is. It is also the voltage across R3, right? But now you have two resistors instead of one. Could you still do that? VL equals the VO or V out at the voltage at the output. We just label this point as output. And when we talk about the voltage node, the voltage at a certain node, we are comparing that voltage to ground. It's actually the voltage between this node and ground, okay, which is the voltage across R2. So if you have another resistor, can we still use this equation? You sure?
You have to change it to...
The current has changed. The current flows through here and here are different this time. So we got this equation from here because they share the same current. But now you have R3 is dividing the current in two branches. So you cannot use this equation anymore. So in that case, if we still want to use the voltage divider theory, what should we do? We just combine these two resistors as one, right? Got equivalent resistance. Then it becomes the same circuit as we just did. Okay? So for this case, it will be slightly different. So VL equals what? Just use the voltage divider theory we have covered. Simplify all the process. So VL equals, you use VI times the voltage at the output, which is VI times the resistance at the output, which is R2 in parallel with R3 this time, not R2 anymore. We have to use R2 in parallel with R3 to replace R2. Because that reflects the fact, whatever you have here. Now the output resistance has changed. And R1 plus R2 in parallel with R3. So this is correct for this circuit, if you have R3 in there. Any questions on this? All right, we'll move faster because so many things to cover and 2 homework assignments due. I have little control over it. The good thing is everything's recorded, so you can always revisit everything if you have time. Okay. Hope you'll have time to watch it after the class. So current divider, R1, R2, and we label the current here as I1, here as I2. And you got an overall resistance here, which is called R equivalent. It's the equivalent resistance. And because this current flows through a black box, which is include the 2 parallel resistors at 1 black box as R equivalent, we can calculate it using the equation we covered last Friday. So current flow through a resistor box like this will cause a voltage drop. So you are getting, if we ground here, you are getting a V here, right? You're getting a V here. And for the current divider circuit, you'll see this in tutorial 3 homework, sorry I forgot. But if it's asking about the basics of the current divider, why is this valid? It's because you have the voltage, the main branch voltage equals every single branch's voltage because it's the same node. Like I said, it's just the same metal piece. Voltage here equals voltage here equals voltage here, voltage here. Right? Same voltage everywhere. It's the same metal. You can melt it. The metal, you can melt it, and it's going to shrink to 1 voltage node. Just 1 metal piece. So same voltage, same voltage, same voltage. So what's happening is I times, that's the overall current, the total current, times the total resistance, which is a black box resistance. Just treat it as 1 huge resistor. That equals to V. And also R1 times I1, which is the branch voltage. And that equals R2 times I2 as well. So all the voltages are equal. All right, and now we can start transforming this equation to the current divider equation. So what's happening is I times R equivalent, which is the 2 resistors. So R equivalent equals R1 in parallel with R2. Okay, and as we calculated last Friday. So this equals R1 times R2 over R1 plus R2. You can refer back to the notes or the videos from Friday or Wednesday last week. So that's the parallel resistance. So I times R1, R2, R1 plus R2 equals R1 times I1. Because of the current divider, the total current is given. The current divider is trying to let you calculate the branch currents. So this is the branch current. I1 becomes, just cancel R1, okay? So that equals the overall I times R2 over R1 plus R2. I can find out very interestingly, for voltage dividers, if you only have R2 here, right? Only R2 here. So the VL equals VI times R2 over the overall resistance. So that's the total voltage. So one quick method that I can memorize, or you can remember the conclusion here, which is, the resistance ratio equals the voltage ratio, if they have the same current. Or the voltage ratio equals the resistance ratio, right? So R2, which is this node's resistance compared to ground, okay, times R2 equals the voltage across it. Okay, for the current divider, it becomes different. if you are willing to find out the current flow through this resistor, you have to multiply the resistance of the other branch, because you got this resistor canceled from the equation. Could you remember that? It's just a quick way to memorize it. Even though I'm not asking to memorize it, but in future, if you're going to apply current divider or voltage divider equations for calculation, you can do it really fast. So for this one, you just if you want to calculate the voltage across this guy, you just put this resistor on the top. Okay? But here, if you want to calculate the current flow through this resistor, you have to put the other resistance on the top. Because
if you were doing like 3...
Yeah, I'm going to go through that right now, okay? So multiple resistors for the current divider. It just follow this equation. It won't be 2 anymore. It will be more complicated, but still the same equation. So for example, we draw a circuit. If you don't want to combine the parallel resistors, R1, R2, R3, I1, I2, I3, that's I, right? If I add more resistors, it's not changing, is it changing the voltage status? It's not changing the status, it's always the same voltage across every single resistor and the main branch as well. However, the voltage will change, right? But they remain the same. The changes, they all change, right? So for this one, if you treat this guy as a black box, you flow a current through that black box, you're getting a voltage drop, and it's the same voltage. So I times the equivalent resistance of the black box. It's just a different equation to calculate the equivalent resistance for multiple resistors instead of 2. And this equals V, right? This equals V, and the V is the same V across every resistor. That will be I1 times R1, and I2 times R2, and I3 times R3. You can keep adding resistors, it's going to be the same equation. So R equivalent in this case equals, as we derived last week, you can find out from the notes. This equals 1 over R1 plus 1 over R2 plus 1 over R3. Right? Okay. Refer to the notes if you want to find out how we derive it. So I times equals I1 times R1. For example, we are calculating I1. In that case, I1 equals what? Just I times 1 over R1 plus R2 plus R3 times R. 1. Right? Any questions on this? So these solves a bunch of problems from the tutorial, I believe. It's page 3. All right. Any questions before we move forward? Good? Okay. Calculate the currents in the resistive network. It's the same method. You just have to transform the resistor network into a different look. R1, R4, R8, R7, R6, R3, R2, R5, I6, I8. So this is labeled as I8, and this is I6. This is I source, right? It's asking for what? Asking for calculate I2, I3, I6, I8. All the resistance are given. Okay, and the current source is given as well, so you can easily calculate everything. Okay, so it's asking you to calculate I2. Doesn't matter, we are not specifying which current to calculate because you can calculate every single current if I just show you how to do it. All right, so the resistors are given and the circuit is solved. No variables. You got a current, you got all the resistors, it's done. Okay, so now let's see how we calculate it. How do we do it? Equivalent, yeah, equivalent what? Equivalent resistance, yes, yes. So when I look at it, I'm not seeing all the complicated networks like that. So when I look at it, the first thing I want to do is combine the parallel resistor, just combine to one parallel resistance, right? It's the R6 in parallel with R7, which is R6 times R7 over R6 plus R7, right? You have used this one for many times. So you just combine these two, you got one resistor, you got one resistor. Okay, got one resistor. And what's next? Because this one will be, this resistor will replace the two parallel resistors and connect to here.
Would you put that in series with
Yeah, put in series with this guy, right? And then these two will be in series. And you add them together and you combine these two into one. So like a parallel, series, parallel, series, parallel, done. Three in series. Okay? If you convert everything in three in because if you just hide here and you look into that network, everything here is just a series and parallel resistors combine everything to one. If everything in the black box over here combine to one resistor and you replace everything here as one resistor, eventually it's gonna be one resistor combined as our equivalent. Start getting like 1, 2, 3 resistors in series, and you use a current. You can easily calculate the voltage drops here and here. So you got voltages. Is everybody following? No? You are? But what about other people? Do you want me to go slower? You? Slower or? Okay, let's do it. So I'm going to convert it step by step, okay? We still have time, it's okay. So first we combine these two. Okay, so this becomes this is R6 in parallel with R7. And that's R8. This is R3, R4, R2, R5, R1. Okay, first step. Second step. What's the second step? You combine these two as one series. R3, and this becomes R8 plus R6 in parallel with R7, right? Because in series. And then in parallel with R3. So next will be this. And this resistor becomes R3 in parallel with R8 plus R6 in parallel with R7. Okay. Next. And it's R4, it's R2, R5, R1. Next. R5, R1, R2, and this is R4, plus R3 in parallel with R8 plus R6 in parallel with R7. Like that. All right, next. R1, R5, and this is this in parallel with this. So it's R2 in parallel with R4 plus R3 in parallel with R8 plus R6 in parallel with R7. Okay, so let's call this R X, for example. So what's next? It's probably asking you to calculate all the branch currents. Big ground here. Let's come back to this original circuit. It's over here. Oh, let's keep it consistent. RE equivalent, RE equivalent, REQ. So that's R equivalent to replace everything over here. Now let me ask you a question. What's the voltage here? How can we calculate the voltage at that node? That will be the next step. Let me tell you. That will be the next step. If I replace everything with this REQ, and I calculate the voltage here, definitely I can do it because I have a current, I have all the resistance. Definitely I can calculate the voltage here, right? Okay. If I find out the voltage here, is the voltage here equal to the voltage of this node with all the other resistors, original resistors? Do they have the same voltage? Think about it one more time. So I either have all the original resistors in the circuit, or I converted everything to this equivalent resistor, just 3 resistors in the circuit instead of a lot of other ones, the original ones. But I use the equivalent resistor, and then let's see how to calculate the voltage first before we move forward. Okay, so here's the voltage I'm asking for. Okay, voltage. What is the voltage? If I ground here, this is I, right? So the voltage here will be the same I. So the voltage here will be the current flow through these 2 resistors combined. So V equals I times R equivalent time plus R5. That'll be the voltage. So I'm getting the voltage here as this node. So if you compare the original circuit, still the same node. Either using the original circuit or use the equivalent resistor, am I getting the same voltage here? Am I getting the same voltage? Just at this point. It should be the same voltage because it's the same resistor. It's the same resistor. The only thing determines the voltage is the resistance. Because you got a current, it's the same current. Another question here. The current flows through here and here. Is it going to be changed if I change the resistance here into the equivalent resistance? Is this current being changed? No, it's the current source not being changed. Okay? And also another question here is the current flow through the equivalent resistor, is the current equals the current flows through the entire black box? Do they have the same current? If I use either the black box, the overall current flows through the black box. For example, the current flows through from here into the black box, or the current flows through the equivalent resistor. If I replace the black box with the equivalent resistor, are these 2 currents the same? They are, because they are the same resistance. So if I find a voltage here by using the equivalent resistance, it's going to be the same voltage at this node in the original circuit. Now things becomes easier. If I have the voltage here, what you can do? It just put this voltage back into the original circuit. You know the resistance here, okay? Can you calculate the current here? Yes. Voltage divided by the resistance. If you know the current here, do you know the current, the overall current? It's just this current. That's the total current. It's gonna be this current. Okay? You know the overall total current, you know this branch current, can you calculate this current? Yes. If you know this current, can you calculate the voltage drop? Yes. If you know the voltage here, yes, definitely, since you just calculated the voltage here. Can you find out the voltage here? Yes, just minus the voltage drop across this resistor. So you can get a voltage here, it's given. Now it's calculated, not given, it's calculated. If you know the voltage here, can you calculate the current here? Yes, just voltage divided by the resistance, you get the, oh, have to be careful. If you're ground here, and this point is not ground, keep in mind. You have to take the resistance and voltage drop across this resistor into account. It's making things complicated. But are you guys getting it?
So for our equivalent circuit,
Yeah.
would the current flowing through R1, R equivalent, and R5 all be the same, which is just 21.5 milliamps?
Yes, because that's the same main branch current. Yes.
Okay.
Same current, same current. That's a good point. Since you have the same current here and here, you don't have to, since you know, so this current is the same as this one, right? So just times the current here, you can get a voltage drop. Because you know this is 0 volts. You can definitely find the voltage here. Am I losing anybody? Just come back to the video and watch it. I know it's getting a bit more complicated. But if you see what I did it just basically get a voltage, you get a current, you got a current, you got another current, you got another current, you got a voltage drop, you got a voltage drop. Since this is calculated, you drop it, you got a voltage here, you got a current, so you got this current, and you got a voltage drop, and you got this voltage, and you got a current, same voltage, current. So everything is calculated, everything is done. Just by finding out the equivalent resistance at the first place. If you find this equivalent resistance, all the voltages and currents can be calculated just following the method I just showed you. Watch the video if you cannot follow, okay? Shouldn't be that difficult. And you can always ask me questions through sending me an email. Another thing to talk about, and it's actually asking you a question regarding the current divider theory. So the conceptual basis for a simple current divider circuit is what? It gives you 4 options. So you are going to select the one I just told you, right? So what's the basis of the current divider theory? It's basically just the I times the equivalent resistance, which is getting the V here. That V equals all the branch voltages, the same voltage, because they have the same voltage. Okay. Another one, delta to Y equivalence resistor network. Okay. Let's see how I did it. It's boring to solve that resistor network, but it's just it's very simple, just follow the equations. R1, R2, R3, R4, R5, R7, R8, R6, and a resistor R9. Two more. Jeez. R10, R11. All right. Delta to Y conversion. So this is delta, it's a triangle. It's asking to convert it into a Y-shaped or T-shaped. So the way I do it is just follow that workflow. So I label ABC. I'm going to show you why do we label ABC. Just label ABC in the counterclockwise manner. So for example, I label here as A, because counterclockwise is this direction. No. Wait, is that clockwise? Yeah, clockwise actually. A, B, C. Oh, counterclockwise, this direction. Counterclockwise, A, B, C. So we are converting this triangle now, okay? Converting this triangle now. Why do we have to convert it? Because it's just trying to simplify it. It's easier to find out the parallel resistance. Because right now it's just getting all the in parallel, sometimes in series, it's difficult to solve it. So we're going to convert this triangle into a T-shaped to simplify it. So the first thing you want to do is label it counterclockwise. Start from a point, like for example here, A, B, C, counterclockwise. And then because you are using this one as AC, you always start from the side called AC. What's that?
Is the which one is you label as AC or the direction counterclockwise?
Doesn't matter. No. Okay, good question. A, B, C. Let's just label it that way. But eventually you'll find out it depending on which side you want to split into two resistors, and you name that side to be AC. I know. Yeah. Just memorize it. I didn't memorize it as well. I didn't even learn it in undergraduate. When I was looking at this problem, I Googled it. I never used it in real world problems. Anyway, just asking you guys to play with the numbers. Okay, it's easy to follow though. Let's just remember, and you are allowed to bring a cheat sheet during the exam, right? So one page, the US letter page, front and back. So definitely, I highly recommend, since I couldn't remember as well, I'm going to write down the equations. You just put the equations on the cheat sheet during exam. Nobody is required to memorize everything like this. So the goal is to convert this triangle into a T-shaped resistor network, which is like this. See, here's AC, okay? I'm splitting AC here. So I'm treating AC as a top bar of the T or Y. Let's just say T because it's more like a T. So that's, remember here's AC, right? AC. And you have to name this resistor. If this resistor closer to A, you have to name it as RA, and this has to be RC. So the other one is like this, it's RB, right? That's the terminal B. A, B, C, A, B, C, counterclockwise, A, B, C, A, B, C. And AC is the one you want to split it. So if you want to split this resistor, just name this as AC. Right? So now things becomes making more sense. Why we have to do that? Because the equation uses all the labels to calculate a certain resistance. So for example, these resistors are given, right? And we are, if we label it, the resistance between A and C will be named as AC, RAC. That easy to label since it's between A and C. So what's this resistance though? R what? RAB. What is this? RBC. Okay? Because this is the original circuit, so all these resistors are given, right? So now I want to convert to another resistor network. So the thing is, you need to know what are RA, RB, and RCs. Okay? So now let's write down the equations. RA equals RAB times RAC. So it's basically just the combination of this resistance, RA, with B and C, right? RAB and RAC. And divided by the overall resistance of all the three resistance added together. RAB plus RAC plus RBC. You'll have the same denominator for all the resistance, RA, RB, and RC. So RB is what? I'll let you guys tell me. So denominator will be what? Same. Numerator, just use this one combined with the other ones, right? So it's R what?
AB times BC.
Yes. What about RC? Same at the bottom. RAB plus RAC plus RBC. Right? Top, RAC times RBC. That's it. Then just a lot of calculations. Let's try one example here. 5, page 6. So let's just look at this circuit.
So, would you just replace your R3, R4, and R2s with your RA, RB, RC?
Yeah.
Okay.
Yeah, I'm going to show you the circuit, the converted circuit, really quick. Okay? It's basically just to remove all the resistors and move everything here, the 3 terminals, into the 3 terminals here. Okay, just grab it and move it to the 3 terminals. Just connect A to A, B to B, C to C, and remove all the 3 resistors. We'll do it together. So now, let's calculate it. Just stick with it. So what are the resistance? R234. 234 from the example. So 2 is 30 ohms. 3 is 15 ohms. 4 is 55 ohms. Okay, so what is RA? RA will be AB, 30 ohms, times AC, 55 ohms, over 70 over 100. And that is 16.5 ohms, which is RA. RB, RAB times RBC. AB is 30 ohms. BC is 15 ohms. Same. It's going to be 450 over 100, which is 4.5 ohms. For RC, it's here, right? RC is RAC, which is 50 ohms times BC is 15 ohms over 100. What is that value? Five times 15, 825 over 100, which is 8.25 ohms. Okay, so now these 3 resistors are calculated. So the next step is to move it back to the circuit, and I'm going to show you how to do it, how to convert it to an equivalent circuit with the 3 resistors like this. So first, you started drawing from the source, same routine. Don't draw anything here because all the resistors will be replaced, right? You got 2 here, So I'm not doing anything for the bottom triangle. I haven't done that yet, but I believe you are asked to do that. I didn't do anything to this two resistor on the side as well, right? So you got 3 nodes open up, or this area need to be replaced by this guy. Like I said, it's A, B, and C, right? So we're getting AC, got 2 split resistors, which is RA and RC. And in the middle, got an RB. Oh, RB in the middle. It's gonna be like that. Is this helping anything? See if this is simplifying anything. Let's see. It's better than the triangle. What's the next? What's the next to make it looks better? Yeah, let's convert it. You know, just make it straight. So we're getting here. You got RB, right? RB in series. Just draw it straight in a straight way. And what's next? So draw it starting from this point, which is this point right now. You got RC. And now have another triangle. The triangle we haven't converted yet. What about here? RA. Is it better? Is here? Because this whole thing is basically the Y-shaped resistor network that we converted from that triangle. It definitely looks better than the triangle. If we convert this thing to the same resistor like this, we'll be able to use the method that I just showed you over here. So we can keep combining the parallel and series resistors, combine, eventually find an equivalent resistance. Then we find a voltage, we find a current, then we find a voltage, current, voltage, current, like that. Am I going too fast? I am, right? So just grab a paper after the class, grab a paper and rewrite it. Just do whatever I have done. Just record it, just do exactly what I did. That's the way to learn it, okay? As a beginner. Imagine that I wrote everything on the board and erase it. Would you be able to have the chance to write it down? You're busy making notes for the whole class? What's that?
So are you not able to just like add them backwards like we've been doing with normal one? If it's diagonal, you have to convert it into the standard form?
What do you mean by make it backwards?
So like when we were,
Oh.
it's not backwards. When we were doing it like earlier, we had something in parallel, we would like this.
Yeah, like this, right?
Yeah. If it's diagonal, we're just not able to do it.
How do we do it though? Tell me, let's see. Let's try to do it, if that's possible. How? Which one is parallel, which one is series? It's difficult to find. The reason for that is if you, so the way we can do that is because we know clearly about the current when it's getting split, when it's getting merged. For here, it's complicated. So the current flows through here, it's getting split, right? Then it's split again. And then comes over here, split again, and merged again. It's complicated. It's not like as easy as this one. Straightforward. Split, and merge. Here, it's difficult to find the equivalent resistance. You probably are thinking that, hey, let's looking from here, okay? I got a 2 resistor from here, and got another resistor. So what I want to do is I want to have these 2 resistors in series or in parallel. They are neither series nor parallel. Why? Because you got another resistor here in parallel with this two. Okay, it's just difficult. There's no way to easily do the parallel and series resistors.
Okay, that makes sense.
Yeah, because after this node, it just couldn't move forward. Split in parallel, you're thinking, hey, we can combine these two resistors as a parallel resistor. Not actually, because you got current split here again, and then this comes back. It's making things complicated. So I have to convert it to the Y shaped like this. If we move forward with this circuit, okay, so what you want to do is, if you just follow the same method we just did, which one will label as AC? Which side would you like to label as AC? Let's just do this. AC, always the side. The side is AC, right? It doesn't matter. You can use this as AC. It doesn't matter. It's going to be the same, but the solution uses the side here, the longer side of the triangle as AC. It's okay. So it's counterclockwise, right? A, B, C, counterclockwise. So this resistor will be RAB, right? Because it's in between A and B. And this will be RBC. And this will be RAC. And these resistors are given in the problem. The original circuit is given. Okay? And then you use, let's see, how we want to convert the circuit, how it looks. AC is the longer side. I want to split A and C, right? So this is RA because it's closer to A. It's RC because closer to C. And in the middle, we got RB. And this is B. Okay? You could definitely calculate these resistance by using the long equations you put on the cheat sheet. What's next? I'm not doing the calculation again. This is going to cover more problem. I have 4 minutes left. So for this one, you definitely want to replace the triangle with, let's just label prime here. Okay? Replace it. Just grab, take it out, and put it back in. It's RB, RA, RC. Okay. Leave it open for now. Right? Because you are replacing the triangle with something else. So this is A, B, C. Okay, what's next? Just got the T-shaped or Y-shaped resistors into it. It's RB prime, RA prime, RC prime. Okay, like that. Page 8. Okay, can we convert it to a better looking resistor network? Yes.
What is the prime notation for?
Oh, prime, because I don't want to have the same RA or RBRCs. Just want to differentiate it. RC, so RC, RA prime here. RB prime. RC prime. RA. A lot better, right? What to do next? Series, series, series. Oh, sorry. Series, series, parallel. Okay? You got one resistor for this black box. You got a series resistor. I got a voltage here. Can you get a voltage here? Yes. What's the theory you want to use? The voltage divider theory. You ground here. You got a voltage here. Then everything solved. Why? You know the voltage. You know the resistance. Resistance. You know it. You can get the current, and everything. All right. See you on Friday.